There she is. Hey, Lily. Give me a second to get the other camera going, okay?
All right.
Glad to hear your voice. Sorry you don't feel well, sweet pea. That's no fun.
Yeah.
Yeah, been having a heck of a time. All right, you guys, settle into getting ready for the next class, okay? Yes, hold on.
But one last chance to document the degree.
You see the room now? Yes. Okay. I'm grabbing a drink and then we're gonna start. So you guys need to throw all your last time over your tray. Come on over to the back.
Bring some more to. Would you like some more, Dave? Would you like some more, Dave?
Spend your coins over there.
Why not?
All right, you ready, guys? Come on. I know everybody's still squeezing their bottles over there. I know that sounded weird, Lily, but that's what they're doing. Squeezing bottles. Come on, volume up. All right. They're coming. They're all grabbing their lunch. Oh. Hello, Piper. Hello, Piper. Yes, your sister. Who doesn't? Poor thing. I got a bunch of kiddos that just, why is Liam out? Do you know? Do you know? He wasn't? So Piper's not feeling well, Liam's not feeling well, Jack's not feeling well, Lily's not feeling well. This is fun. Welcome to fall, I guess. Closer we get to winter, the weirder it gets.
Flu going around.
Yeah, I know. Yucky flu going around. Say what?
Stupid flu.
Yeah. Do you have flu?
Yes.
Oh, man, I'm sorry.
Yeah.
That's awful.
It also hit Savannah too.
Oh, yeah. I saw that Jackie had her going.
Yeah.
That's fun. Goodness sakes. That's a rough.
Yeah, I know, it really sucks.
I'm sorry. Ugh. Well, it's a thing right now. It's going around. So I guess that means you've done away with the myth of unsocialized homeschoolers, huh? You catch communicable diseases. Everybody knows that's a lie. All right. Are we all here? Actually, you can open him. He's good. You can open. I usually let him out during lab, but we were busy. All right. So everybody's good. We're going to start. Who am I missing? Somebody. Nope. All right. Drew, you want to come sit where Jack usually sits, or are you good there? Eating. You're eating. All right. So we're going to talk about the atmosphere today, and you guys have an idea about atmospheric pressure and temperature relationships after that lab. I like that lab. It's easy to do, and you can really see, you can see what's happening right then and there. It's not like a lab you have to wait a long time to see, you know, the reaction in your experiment. It's pretty quick. All right, so here we go. I like of all these images, the cats and Drew, sit down. Drew, don't feed people. It's like zoo animals. Don't feed people. Don't feed the animals. All right. I like the bouncing cats and dogs best. They're my favorite. It's raining cats and dogs. All right. So we will talk about, there we go, weather versus climate. You guys know this, I think. Hopefully by now you know this, that weather is day to day, can change within hours or minutes, and climate is an average. Does anybody know how many years climate's the average of how many years? I think it's 30 if I'm not wrong. So it's a lot of years, and they take all the averages, different seasons, whatnot. And that way you get an average weather pattern and temperature for time of year for a specific area. So then when you are moving somewhere, you can consider climate probably more than, well, consider both. But you may, if you like subtropical, You might not like living in the tundra. I wouldn't like living in the tundra, you know? Even though you may have days in the subtropical where you have snow, it's still not the same thing, right? So let's see. Atmosphere. So your atmosphere is this thin layer that surrounds the earth, and it's got all of the different gases in it, and it also has some solid particles in it and some water within it, and it's being held to earth how? James? Gravity is pulling it to earth just like it pulls everything else to earth. It's kind of weird to think about gravity pulling on air, but it does. And that's why when we talked about just a little bit ago, altitude and pressure. Altitude and pressure are linked because the higher you go, if you think about a column of molecules, the person at the bottom is going to have more. Anybody know the story of Yertle the turtle? It's a Seuss story. You know Yertle the turtle? What happened in Yertle the turtle? Do you remember?
These stacked turtles get really high up on turtles and falls because somebody gets crushed by turtles.
The dude at the bottom sneezes and causes the whole stack to fall, right?
I was also complaining about.
Yeah, everybody was whining and complaining because Yertle wanted to be the highest turtle in the pond because he said he was the king of all he could see. So the higher he got, the more he could see. So the little turtles on the bottom were under a great amount of pressure because there were so many turtles stacked on top of them. And you can think of air molecules in a column the same way. The atmosphere is also important because it protects us from the sun's heat and UV rays to a degree. Obviously, UV rays get through, but a lot of them are blocked in our stratospheric layer. So folks that look like me are not friends with UV rays. Obviously, UV rays are what give you the sunburn and whatnot. So
They can also kill you potentially.
yes, because they give you skin cancer, but it's essential that we have all of these different wavelengths of light, and we'll get into those next year, especially if you do physical science. There's a lot of like study of light and sound. It's really kind of fun. So we've got, moving on, this dude. I looked up ancient Greek cartoon and I got him, but he kind of looked like Santa leaving a sauna. That's what I thought. Doesn't he kind of look like Santa leaving a sauna? Like he's like, whoo, it was hot in there. That's my thought. Anyway, so the ancient Greeks believed that air was an element and it couldn't be broken down. What were the ancient Greeks' elements? Who knows what they were? Alex?
Fire, water, earth, and air.
Fire, water, earth, and air. So they thought these were elements. Air is an element. Fire is an element. Water is an element. Earth is an element. And they used to consider those elements. We know better now because we know that air is made up of a combination of gases. Some are compounds, some are just molecular but elemental. And like think about oxygen. Does oxygen like to be alone or what?
Always comes as O2 or O3.
Yeah, oxygen is not good at being lonely. He likes to have a buddy just to be stable. So it's usually O2. So that's elemental gas because there's nothing else combined with it, but it's molecular in that it has two atoms. Now CO2, that's going to be a compound, right? Because now you've got different types of elements / atoms together making up a molecule. And we know that these gases form our atmosphere and it's not an element. So atmospheric composition. So we have percentages of nitrogen and oxygen. Who knows the percentage of nitrogen, James? 78%. Excellent. And who knows oxygens? Bailey. Just doing the math. Close. Try. Wait, you almost got it. Try one more time. Not 11. No, your ones is right. Your tens is wrong. 21, Bailey, you got it. All right, 20. Good job, girl. 21% oxygen, 1% everything else. So look at this. She's like, shut up, math king over here. Alex is a human calculator. If you've not done chemistry with Alex, you've not experienced the human calculator, and it's a little terrifying.
Equation by a lot of sugar high.
Yeah, and next year in physical science, that'll be scary. No, I don't ever do that. Look, when your twin sister says, please don't give him sugar, you have to listen. She knows.
Make sure he's actually slept, because sleep deprivation will make him crazy.
Excellent. So anyway, back to the composition, shh, guys, back to the composition of the atmosphere. So there's more nitrogen than anything, which is kind of weird because you don't think about it because your body doesn't use nitrogen like it uses oxygen. There's nitrogen in compounds, sure, but your body doesn't use it like it uses oxygen. There's a nitrogen cycle in the ecosystem. It's a natural part of the way Earth functions, and that's where a lot of that nitrogen gets cycled around. And it's essential for that cycle, although it's not something that you do when you breathe in and out. So, but you're breathing in nitrogen every time you breathe. You're just not using it. Oh, never mind. I have nothing to say. No. Yes.
Everything does. It's one of the prime components of organic compounds.
Remember Schnapps? What was that? CHN
Carbon,
hydrogen,
nitrogen,
Oxygen.
oxygen, and I believe
phosphorus, and one more was the S.
sulfur.
Yes, those are the main elements used in biological compounds. Very good, Alex. That was awesome. You remember all of them. I'm impressed. Now Rico's here. Rico's here because you need to remember there's more nitrogen than anything, and oxygen is second, and then all of this other stuff is only 1%, which is an itty bitty bit when you think about all the water vapor makes all those clouds you see. Think about just the water in the atmosphere, storms, you've seen storms come through, dump tons of rain, cause floods. That's still part of the 1%, not even 1%, part of the 1%. Do y'all know that some places will put nitrogen in tires? Have you seen that? That's about like the most common use of like just plain nitrogen besides liquid nitrogen that you might see day to day.
It's also used in potato chip bags to ensure freshness.
There you go. Didn't know they stuck it in there. All kinds of
Because
stuff.
chemically is inert. It doesn't react.
That's-
nearly anything.
Yep. Excellent. All right. So key atmospheric gases. So what is here? This is water in a gaseous form, especially when it's below boiling temperature, spread through the atmosphere. Milo. Close. What are clouds made of? Drew, I didn't call on you. Close. Parker, do you know? Chloe, do you know? Caitlin? Water vapor. Parker, good deal. All right. Water vapor is what we're looking for here. So water vapor, especially in a gaseous form. Now, when you have a pot boiling on the stove and you see the white stuff, that's the water vapor. The steam, you don't see. That's before. The water vapor is, you've got some water molecules that are stuck to others, they're coalesced, so you can see it like a cloud. When it's all broken up and they're really not touching much, that's the steam, and that's the stuff you can't see, and it is super hot, right? That's probably usually in the middle of that column of white stuff. Yeah.
I found that if you look through steam, you can see on the other side,
Mhm.
light's a little altered from the heat.
Yeah, it's distorted, and that's
It's got an
through.
interesting shadow.
Yeah, that we'll talk in next year when we do physical science. We'll go over why that's true.
I'll have to try that.
It's distorting the beam of light, and if you think about what's going on there, you can probably figure out why, but that's on next year's topic. So the amount of water vapor at any given time or place changes constantly. Percentages change with seasons, right? Altitude and all kinds of other surface features. If you're near water, you probably have more humidity, more water vapor, especially if you're near water on a warm day, right? And the level of carbon dioxide and water vapor regulate the amounts of energy in the atmosphere, but this is an interesting one to think about. Water is the only substance that exists in the atmosphere in 3 states of matter. The only one. You can have solid water, which looks like what? Ice. And liquid water, which we know, and then water vapor. So you can have all those in the atmosphere at one time.
It's the only substance to be found anywhere on Earth, not just the atmosphere, in all 3 stages.
In regular, under regular atmospheric conditions and whatnot.
Wait, are you talking about only naturally?
Yeah.
Under regular atmospheric conditions. Yeah. Mhm. There is. This is true. But solid oxygen, where's that? Yeah. See?
Somewhere.
Mm-hmm. It's interesting. Do you ever see that? That's the question, like, you've been in the city, right? You've seen pigeons. You ever seen a baby pigeon? I've never seen a baby pigeon, but they're there. All right, so atmospheric gases. So these are things under this topic of atmospheric gases. We're talking about solids in the atmosphere. I got 3 solids here. All right. First one, I'm talking about something that's carried up by wind. The second one is carried up by ocean spray. And the third one is found in the form of hail and snow. Who can tell me what that first one is? James. Dust is right. It is dust. Where are you, James? I know you're on here somewhere. There. All right. And then what's the second thing, Bailey? Salt. That's right. Salt is picked up and moved around. If you ever go anywhere near the ocean, sometimes you can see buildings that have salt spray on them and whatnot, and they're not like in the water, obviously, so it's blown up on them. And the last one is everybody together.
Ice.
Ice, right, okay, so there we go. That's an easy one. Now, ozone, let's talk about ozone for a minute. So ozone is a gas formed by a third, what kind of atom to this molecule? Anybody know what ozone's made of? Do you know, Sky? Do you know, Caitlin? Chloe?
It's something.
Ozone.
Something.
Alex, what is it?
It's a third oxygen molecule added to an O2.
Yes.
Third oxygen atom added to an O2 molecule.
This
It's
is right.
O3.
Okay, yeah. So oxygen, like we said, likes to hang out with a buddy. He's always going around as O2. Sometimes he'll go around as O3. He likes 2 buddies, hangs out with 2 buddies and meets more friends. So it's just the way oxygen is built, the way the molecule is built allows for another one to snap on there. Think about the way, it's just like Legos. Think about, Yep.
They all want one more, so technically
How come
you
they only
could have
form
a
up?
chance.
they don't only form up on the ozone layer. You can have ozone down
Well,
here as well.
Electricity is a great way to cause it.
Yeah, that's a good point. So Alex brings up, you can get ozone with electricity.
Like
Um,
oftentimes from a lightning strike or from
Mhm.
static, you will smell
Yep,
ozone.
You can smell it. It has a very specific smell. Actually, your Nana's first hot tub had something that released ozone into the water. I'm not even sure. I don't remember why, but anyway, so, well, there's a lot down here, but it does really well up there in the atmosphere. And so there's an ozone layer, right? And it has spots in it that are thinner than others. So all of these layers of the atmosphere, they're like a blanket around Earth, right? Each one, but they don't have the same thickness, so to say. In some places, they're thinner than others. The ozone, though, caused concern in like the late 80s, early 90s, because they found this hole in it and everybody's panicked. There's a hole in the ozone, we are going to die. So the problem at the time were that they said were these propellants used in stuff like hairspray, also oddly enough, like asthma inhalers. So they were chlorofluorocarbons, CFCs. That's what we didn't want. So hairspray, as you know, in the late 80s, early 90s was like essential for everyone because, you know, the hair was like, there's up here. And I mean, I did it. We all did it. We all had the hair. It was the 80s hair and everybody was kind of panicked because they took away our rave hairspray. But if they went from the cans, like a spray paint style can, you know, woo, to the little, I really think that's why the hairstyles changed in the late 80s because nobody could do it anymore. So those little pumpy ones, now they figured out how to make the spray ones that don't contain CFCs. The asthma inhalers too, that they spray the propellant in, right? I mean, the propellant sprays in the medicine. They took those away too, and they changed them to CFC free ones. But not everybody, not every country did all this stuff. The US did it, but not every country did it. Canada didn't do it, yes. And so people who are longtime asthmatics, like my husband, he complained as soon as those CFC free inhalers came out. He's like, these do not work as well. And there were people buying their asthma inhalers from other countries because they worked better, or they swore they worked better. They've improved things since. But turns out all of the hairspray and all of the asthma inhalers in the world weren't putting nearly enough CFC to deplete the ozone layer as methane was being put up. Does anybody know where the methane is coming from?
Cow farts.
Cow farts is right. Okay. Cow farts are doing more damage to the ozone layer than just about any of this other stuff. And I remember him getting very frustrated with the crappy inhalers, and he actually said, all the asthmatics in the world puffing away don't equal one cow fart. And that has stuck with me for like 10, 15 years because it was hilarious. Not for him. Yeah, yeah, he didn't find it funny, but I did. So do you need a chair over there? Anybody, y'all good? Is there an extra chair or is everybody up? Okay. Somebody was down lower. Milo was down lower, but you're okay now, right? Okay. All right. So ozone layer is thinning. There's things we can do about it. Maybe it's a problem that we're causing. Maybe it's because we have too much beef farming. I don't know. So and that's the thing too. Do you remember a couple years ago when they came out with the it was beef that was, it wasn't 3D printed. It was some kind of, it was cloned. It was cloned meatballs. Do you remember that? They cloned the beef meat cells, the muscle cells, and then created a meatball that was cloned. And one of the ways they were selling it is we can farm less cows and it's better for the environment. Yeah.
Humanity has made great strides. Cloning meatballs.
Mhm.
No.
It was interesting because a lot of people were like, sure, I'd do it. And people, they had people try it and they said, just tastes like a meatball. And then there are other people who were like, I would absolutely not eat that because it's not natural. But then comes the question, does your body know the difference between a cloned cow muscle cell, cloned bovine muscle cell, and a naturally
The body doesn't know anything.
formed?
Right.
Yeah, at a cellular level, when you break down that muscle cell, does your body react any
If
differently?
they're identical cells, then no, because.
Interesting, isn't it?
it's
Yeah.
I don't remember the exact name, but it's the same one as the chemistry law, where no matter the source,
Mm-hmm.
if it's the same chemical formula, it's the same.
Yep, that's it. It's the same as the same. So what are we looking at here? Pressure is what? It's a physical, Bailey. Yes, it's a physical force exerted over an object. Yep, or over an area. So I think your book said force over an object or the measure of force applied over a unit. Those are fine. But if you remember, pressure is force applied over an area. That's pretty accurate. Yeah.
Question.
Hmm.
So if you had a perfect circle,
Mhm.
or like a perfect 100% down to the atom, perfect like orb.
Orb or circle, 3D or 2D?
I don't know.
Okay. I'm not sure where this is going, but all right. Okay.
Wouldn't be able to break it any specific point. Whatever single point.
I guess it depends where you're putting the pressure. You're talking about pressure all the way around?
No, pressure from the inside.
Oh, from the inside out. That's a great question.
I,
You have to break the molecular bonds, I guess.
eventually it's gonna break, like, I don't think it can withstand the force of a supernova going off inside of it.
That's true. I think it would depend on what that
Everywhere it
membrane
was.
was, what the membrane was composed of. And is it malleable? Like, is it latex? Or is it copper? Steel, that's different. So this is Rico, because you should always remember that pressure is a force applied over an area. And this will come back in physical science, and it's just a good one to know.
And
So your
also,
air pressure,
remember, don't try and hammer bowling ball pins
Yeah.
into the wall.
yeah, I'm not sure what that was even about. This dude's like, I don't know why you would do that. But anyway, he did. So the weight of air pressing down on a surface is air pressure. Why is it weight and not something else? Why is that word used? Weight. Drew.
His weight is one of the ways that you kind of calculate weight in a way. Like you
How
can say
so?
pounds of force, but so
What is weight? Like just by itself, what's weight?
Weight is the force of gravity on something. Like if you
Gravity on
on
a matter, right? So it's how your mass,
if you drop something from a tower
yeah,
for a couple, like for a fraction of a second, it's going to be putting a certain amount of weight on the ground or it bounces off or goes.
gotcha. So that's important. It's because we're dealing with gravity here that weight is used. So bless you. So how does a barometer work? Barometers are cool. So this is, how does a barometer work? All right. I love these little TED ones. This is a little TED one.
They look worried about it.
Yeah, they do. I don't know why.
I'm very.
I think the joint whatever.
everybody quiet so you can listen, right?
Aristotle famously said, nature fears of empty space, when he claimed that a true vacuum, a space devoid of matter, could not exist because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than water, and the mercury columns stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box or the tube can have a heavy impact.
Yeah, there you go. we don't use, what? Question?
How could you believe that creating a vacuum is possible? You can literally create a vacuum inside of your.
Wait, Drew is asking a question.
How can people think that creating a vacuum is possible? You can create a vacuum inside your mouth.
Ah, see, great question. How do you mean when you create a vacuum inside your mouth?
Close your cheeks, right?
Mhm.
Like everything, and you suck in, you have the air, there's no air inside your teeth, it's gone.
Okay,
There's nothing inside your cheeks.
right. So, oops. So yes, you can create a vacuum inside your mouth, but oh no, that wasn't a thing they thought. So it's, yeah, and also it's interesting, they brought up how the tube, they talked about how it's the tube that's, well, it's sort of like the same thing when you breathe, right? The reason that you pull air into your body, how's that work? What causes the air to suck into your body? James. Your diaphragm, yeah, diaphragm drops down, but what's it create when that happens? Yeah, it creates a vacuum. And so your body pulls in air. And that's the same kind of idea. That's what they were dealing with here. So let's talk about density a bit. So here's these dudes, a column of dudes. Here's my Yertle the turtle column, but it's dudes this time. And the guy up there says, up here, I have little weight on me and I feel low pressure. And that dude says, down here, there's a lot of weight on me and I feel high pressure. I bet he does. So it's the same thing here with your column of air. The more molecules you have, the denser it is. So as your pressure is going to increase, it's increasing in part because it's becoming more dense. What's density? Alex?
It is how much weight there is per volume. It's,
Close. Yeah.
I can't remember if it's weight to volume or volume to weight.
It's basically how much matter is in or mass is in a given volume, right? Very good. Very, very good. So you're used to the pressure of air that air exerts on you. That's what you're used to. And fish are used to a very different pressure.
The reason that you doesn't feel like there's any pressure on you is because you're adapted to it.
Yeah, you're acclimated entirely. Now it's like when you swim to the bottom, anybody ever swum to the bottom of like an 8-foot pool or a 10-foot pool and touch the bottom? What do your ears feel like when that happens? Yeah, what do they feel like, James? Get hurt. Yeah, because those are the smallest bones in your body and the membrane that's your eardrum is really sensitive to stuff like that. And you've increased the pressure. Now, when divers surface, deep sea divers, they have to come up very slowly. Does anyone know what that is or why? Bailey, do you know?
And die.
Yeah, they can get really sick.
They'll expand rapidly because they're on their different atmosphere, and then
There's more.
And it has to do with what?
or
Well,
nitrogen poisoning.
first, there's the nitrogen in their blood will expand.
Mm-hmm.
Two, I wouldn't be able to tell you what it feels like to the bottom of the pool with the eardrums because ear tubes.
Tubes. Yep.
So it would have been plugs and I wouldn't be able to tell how the
Yep.
plugs feel. And I haven't gone swimming since I've had my second tube.
Gosh, Drew.
I understand the whole reason that the deeper you are, the more water is above you.
Mm-hmm.
But there's 10 feet of water above you. That's a lot of weight. How come you don't feel that way?
You do. Your ears are the first thing that feels it.
Yeah,
Like-
your entire body doesn't feel like there's several hundred.
Oh, it does. I mean, when divers go deeper and deeper, they'll feel that. James,
Even if you swim to the bottom. of the
I know.
pool,
that's not enough. You'd have to be much. Yeah.
You need a whole secret license to catch fish that are 30 feet from
Oh,
the water surface.
Do you?
You need to do it at a slower rate so
so that they don't- so that coming up process that makes people sick is called the bends.
Oh, wait.
That's what I call it, getting the bends. So you're used to the pressure that's on you. Fish are used to the pressure that's on them. So what does pressure do with depth? Pressure, Milo, increases with depth. And what about altitude on land? Pressure is going to do what with altitude on land? Caitlin, you can do this one. What happens to air pressure as your altitude increases? The higher you get, what happens to the air pressure? The higher you get, is your air pressure going to be higher or lower when you go up high?
Look at that, look at how much pressure the guy and we're on that.
Your air pressure is gonna get lower, right? So what do you call that kind of relationship when one thing goes opposite the other? Alex?
Inverse.
It's an inverse. That's an inverse relationship.
And
Yep, altitude increases, pressure decreases. Depth increases, and pressure is going to increase. All right, so here's the one to know. There are a gazillion
five.
gas laws. For example, here's a bunch of them. Boyle's Law, Charles' Law, Gay-Lussac's Law. That's not even all the laws. There are more laws than that.
Or
This is the big one.
ideal gas law.
PV equals nRT. See him here? Okay, this is, some people say it's PIVNERT. PV equals nRT. Pressure is the atmospheric pressure. That's P. This is your volume. Pressure times volume is going to equal N, which stands for number of moles. We'll talk about that. Present in a gas. R is your constant that converts the units. So here's your value. That's just a value that you use, kind of like 3.14 is pi, right? And then T is your temperature at Kelvin. And this is algebra. This is your basic algebra. And you do like conversion units and crisscross, kind of like we did in chemistry. And we did that a lot in physical science. So you have a law called your ideal gas law. And this states that the product of the pressure and volume of 1 gram molecule of the ideal gas is equal to the product of the absolute temperature of the gas and universal gas constant. Blah, 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 blah. When we get to really using these, they make sense because you're using them in context of other stuff rather than sort of separated out like this. So what's an ideal gas? Is there any such thing? What's an ideal gas? Any got example, Drew?
Oxygen?
Oxygen? Anybody got an example of what an ideal gas is? Alex?
It's one that follows certain laws that
You're back
don't
there.
really
Chloe.
follow. It,
Yeah.
I believe it's like, it's weightless.
Yeah.
Molecules don't bounce around.
So it's a hypothetical. It's not a real thing. It's a gas whose molecules occupy this negligible space, have no interactions. It's a constant that they use because it's close to what perfect would be, even though it's not a real thing. So then you have this universal gas constant, and that's known as molar universal or ideal gas constant. That's what you're looking at right here. Now, what's a mole? Okay, moles are things you use when you really get into chemistry. A mole is a measure, it's a measurement, and it's the unit of amount in chemistry. So a mole, ooh, there's a typo and you missed it, Alex. I should have a space there. A mole of a substance is, I fixed that, or you call me out. See, right there, space. There you go. So a mole of a substance is defined as the mass of the substance containing the same number of moles. And then we use this number. Use something called Avogadro's number. It's all chemistry. It's like 3.14 is pi. That's where you're going to get stuff like ideal gas constant, Avogadro's number, things like that. What you need to know is PV equals nRT. Even if we aren't going to use that equation right now in class, this is one to memorize for life. It's going to come up again and again. So like I said,
Chemistry, 2 years.
everybody's talking. So yes, the Boyle's Law, Charles' Law, Gay-Lussac's Law, there are more that deal with gases. And a lot of these are like, these two are pretty much inverse of one another. But you get your own law when you state the exact opposite. I don't know how that works. But anyway, there's gonna be a lot of them.
Just says, his name, not the law.
Yeah, of course. Oh yeah, because now your name is in history forever. So density, so proportional to the number of particles of air occupying a particular space varies with temperature. And you can see temperature, pressure, and density. And this makes perfect sense, right? Because you just did it in lab. If you increase the pressure, your density you increase the pressure, your temperature is going to increase. And I mean, you guys just did this. You saw how it works. Okay, so let's talk about sun a little bit. So solar fundamentals. Different areas, these are our 3 different types here of like heat. Wait a minute. Okay, those are your 3, shoot.
I know what the first one.
Yeah, no, everybody knows now because it's too fast. So these are your 3 different types of heat transfer that we're talking about here where the sun is involved. So I let the first one go. So that's radiation. So you're sitting outside and you feel the sun and it's warm, radiation. You're sitting near your heater and it's not blowing air on you. You just it's like a radiator maybe, and it feels warm, radiation. Never mind. Okay. What's the next one where you talk about transfer of energy that occurs when molecules collide? Caitlin?
Conduction.
Yeah. Okay. So let me see. If you're in this room, put your hand on that glass. And if you're over there, put your hand on that table. And Drew, you can do the counter. All right. Now, how does it feel in comparison to your hand? Warmer or cooler?
Like glass.
Okay. Now pick your hand up. Pick your hand up and wave it around in the air. Does that feel warmer or cooler than the surface you touched? Warmer. What do you think is the temperature difference between one and the other?
None.
None is correct.
It's the.
There is zero temperature difference between that cold table and the air. If they're in the same room and they've been there a long time, the ambient temperature should be the same. What happens when you put your hand on a surface is the heat moves out of your hand because it's warmer. Things go from warm to cold, not cold to warm. So that's conduction. That heat just conducted out of your hand and into the surface you touched. That's why if you leave your hand there long enough, you'll warm up the table, right? That spot will be warm. That's conduction, just like electrical conduction, have to be touching. Okay. Now, if you put your hand next to your friend's face real close, you could probably feel, don't do it, but you could probably feel some heat there. That's radiation again. So this last one is going to be convection, and this deals with blowing around. So heat blowing in your house. But it doesn't have, remember fluids, we're talking about air and wind in this case, but remember that liquids are also fluids. Gases and liquids are fluids. And when we get to plate tectonics, there's going to be a lot with convection. And we have an awesome lab involving tomato soup and Ritz crackers. Are y'all listening over there, Cracker? Chloe, you good? All right, temperature versus heat. We talked about temperature. What is it? It is the we already did this one. It's the measure of how rapidly or slowly molecules move, right?
And
That's what temperature is. It's about how rapidly or slowly molecules are moving. It's an old one. So fewer molecules or slower moving molecules are a lower temperature. When you pack more molecules together, like we did in lab, you get a higher temperature, right? And that's because they're closer together. And James said it in lab. What happens when everything's closer together and bumping around?
boingy, boingy, boingy.
Friction, right? Remember this. Remember that temperature is a measure of how rapidly or slowly molecules move around. It has nothing to do with what you feel. Heat, on the other hand, heat is what you feel. So this is heat. I'm not gonna, yeah, there you go. So heat is the transfer of energy that occurs because of a difference in temperature of substances. That's why you felt less heat than your hand. Like the table felt cold to you, that's still a heat, right? It's just a very low heat. So yes, heat flows from hot to cold, always. So these are just some different ways we measure temperature.
Finnish sauna.
Yeah. So you got Celsius, Fahrenheit, Kelvin, Rankine, and Raumur. So yeah, here's your kind of where these things are. You've got Finnish sauna and boiling water. I was in a sauna recently, and one of our little Airbnbs in Cape Breton had a sauna. It was outdoors, and it was cool because it had this giant, like convex, well, concave from our perspective, lens of a window that you could look out into the, it was weird.
It was orange.
But yeah, it was orange, but it got super hot in there and I could only stay for a little bit. And then, you know, room temperature, they're saying it's less than 21. That would be a cold room, let me tell you. If you ran it, no, I guess it's about 21 there, if that's the line. Yeah. I would say probably more like 22, 23. So these are just some ideas, and Kelvin gives you absolute zero. And what's absolute zero? Who knows what that is? Drew?
Absolutely no hot heatness at all. Everything stops moving.
All the molecules stop moving. Do we experience that all the time somewhere? No, it's another hypothetical idea, right? Like,
Die.
yeah, everything, yeah, what would happen then?
A few years ago, I saw something where they kind of achieved that got as close to absolute zero.
Oh, yeah? That's cool.
Time also freezes.
That's what I was about to say. It would have an impact on time as well as having an impact on temperature. So, and pressure and all of that, because all of it's related. And if you get really deep into physics, it's kind of weird to think about what absolute zero is. So again, our temperature versus heat. So we have this temperature at which air must be cooled at constant pressure to reach saturation. And saturation is the point in which air holds as much water vapor as it can. What do we call that? The temperature where air must be cooled at constant pressure to reach saturation. Do we know? Chloe? Dew point. Okay, that's dew point, right. And then, so this other one is obviously what? Caitlin? Condensation. She's like, I'm gonna say it slowly. Yes, so this is when you get rain. All right, so your dew point, we had a very nice dew point, high dew point this morning. We were out there and it was like, there was dew, everything was wet, there was tons of fog. Jason spent a lot of time with the drone out there this morning because the fog came all the way up to the street instead of just down by the river. We usually have a river mist in the morning this time of year, but the fog was crazy. Now, oh, by the way, frost, that's when you have a dew point and then it gets, that's really high for your area and then it gets cold and then you get frost, right? So temperature inversions, we're not going to do much with this, but know that there are times when you have air masses moving in such a way that the warmer air mass is forced under the cooler air mass. And then eventually it's going to get sucked back up. And this can lead to more pollution issues because it's going to take whatever is down closest to the ground and pull it right back up. And that's not super because then it moves around everywhere and it's up too high. And it obviously would affect weather. So wind, what causes wind? Chloe, you know? Wait,
Please?
do you know?
I realized I had the wrong answer, so I was trying to.
Okay. I said, what causes wind? Sky, do you know what causes wind? No? Anybody know? Drew?
I don't think there's one specific cause.
Yeah, there's a general cause.
The movement of Earth.
Not Earth. Well, there's a slight bit, but that's not the big one. James? That's the big one. So you have air masses, right? Big, you can think of it like just blobs of air, right? They're all around in the atmosphere. Some are warmer than others. Have you ever been in a lake? It's kind of interesting. If you're in a lake or a pond or the ocean and you're swimming and one like part of your body feels like it's in cold water and there's like something warm down here and you're like, oh, it's warmer over there, it's cooler over here. Because their water's the same way. It's a fluid again. There'll be warmer parts and cooler parts that shift around. Now, when that happens in a pool, you kind of think, maybe I should get out now. I just hit a warm spot. That's a little different when you're in a swimming pool. But when you're in a lake or something, it's interesting. It's also part of the reason why you have currents in a lake. Remember I mentioned that when they open that dam, a lot of water comes flowing out and that water's coming from the bottom of the lake and it's very cold compared to the water on the top of the river. So that water sinks under and puts an undertow that you can't see beneath the current on top that is warmer. So wind is caused by shifting air masses. So when you have a warm air mass and a cool air mass and they're moving around, they're going to cause lots of wind to occur. So you hear like a warm front is coming in or a cool front, cold fronts bring a ton of wind ahead of them. And then you get this, nice cold front that follows it. And usually that brings in some kind of wetness or storm or weather. So you get high and low pressure areas. Obviously, think about it. The warm air mass is going to have what kind of pressure, higher or lower? Higher. We just did that in lab. And so then you got this high pressure air mass, and it's going to shove the low pressure air mass out of the way. And then you get all this wind moving around. So obviously that also changes with the height in the atmosphere because gravity affects everything. All right. What's number one? Somebody hand up. All right, Chloe. There you go. Number one, troposphere. Oh, I clicked that wrong. Oh, I didn't change yours. I changed the others. That should be number one and number two. But yes, you were right on the first one out there should be, those two are reversed. I fixed it on the other class because I realized arrows are backwards. So yes, okay. And then what comes after? So you got troposphere, stratosphere. What comes next? Caitlin? Mesosphere. Okay, you've done biology. You've seen meso before, haven't you? Yeah, what?
It means middle.
Middle, right. Okay, so yeah, you will see meso a lot in science.
Medi.
Okay, yeah, medi.
Means more middle, but
Yeah, all right. It's one of those Greek and Latin things again. And then what comes after that, Drew? No, not next, thermosphere.
Thermosphere.
Then exosphere, he said. All right, so here's what happens in these different levels. So you have troposphere, that's what we're living in, okay? And it's closest to Earth's surface. It contains most of the mass. Why?
because it's dense.
Yes, yes. Why is it more dense close? You tell me, why is it more dense closer to the surface of the Earth? Think about it.
Say it again, why is air more dense?
Yeah, I asked Sky. Think about it. You have all the pressure and then you got gravity pulling all those air molecules towards the center. So it's more dense because there's more gravity. That's why, yeah. So there's more gravity, so that's why it's more dense. So then let's think. What else does it have? It has, click, all right. General decrease in temperature from bottom to top. Makes sense? Mountains, beach. Upper limit, they call the tropopause. Pause means to stop. Varies in height, and that's what I mean about how the little blankets surrounding the Earth are not the same quote unquote thickness all the way around. All right, so now you got stratosphere. So this made up, mostly you got a lot of concentrated ozone in there. This is the layer that's responsible for absorbing a lot of UV rays. It doesn't absorb them all, right? It's coming through. Now think about it. If you're in the stratosphere and you have a hole in the ozone layer, then you're going to get more UV coming through, right? So that's a concern. Now you've also got temperature gradually increases to the top of the layer. Same thing as in the troposphere, right? And then the upper limit is called the stratopause because it stops. And it's about 50 kilometers above Earth's surface. And now you have the mesosphere. All right, mesosphere, no concentrated ozone. Temperature just generally decreases. Why is it decreasing? It's getting further from Earth. Why do you think it's decreasing in temperature? Bailey? There's less pressure. That's a whole lot of it. Yes, absolutely. There's less pressure. So therefore your temperature is going down. And they call the upper limit the mesopause, not the menopause. That's different. The mesopause, right? There you go. The mesopause. All right, makes perfect sense because that's where your layer stops. And then we have the thermosphere. Contains a tiny portion of the Earth's atmosphere. Less pressure, less molecules, not much up there. And the temperature is going to increase with the height to more than 1,000 degrees. Why? What's going on now?
I know.
Drew, why?
Because now there's nothing stopping all of the sun's, bringing back to, we're just gonna try.
Okay, anybody want to add anything to that?
No.
No?
I'm still thinking about the code meatball thing.
I know, you can look it up when you get home, Google it, it's really weird. So it gets to more than 1,000 degrees, but here's the thing.
Oh,
What?
so if I made like how high is that again?
It's high, the thermosphere is 80 to 90 to 800 kilometers,
So
a very
I
big
got
one.
an
Mhm.
800-kilometer long like stick. Could I like fry a hot dog or marshmallow?
No, well, I don't think so, and here's why. Although it can get to more than 1,000 degrees, the molecules are so far apart that it would not feel warm to you if you had to stick your hand out. Like if you were in a spatial and you could stick your hand out, which you can't do.
You have a radioactive.
It wouldn't feel warm because the molecules are so far apart. What were you gonna say?
You can cook a steak, but it's gonna be Pittsburgh. And you're gonna have to thaw it out.
Yeah, there you go. So lastly, we have our exosphere. Exo means outermost layer of Earth's atmosphere, and it's full of your lightest gases, which are going to be helium and hydrogen. Yet helium is 1 on the periodic table, right? It's itty bitty. Helium doesn't have what?
It's hydrogen that doesn't have the neutron.
Is it? That's helium.
What's above?
Hydrogen
yeah.
is number one.
Yes, hydrogen is
helium
one.
number two.
Yeah, didn't I say hydrogen was one?
You said,
I said hydrogen. Yeah. Oh, maybe we're all crazy.
And space.
Yes, basically, it has almost no mass, hydrogen. And then helium comes in at number 2. Hydrogen and helium, if you turn hydrogen into helium, what's it called? Do you know?
fusion.
Hydrogen.
Fusion, yeah. And then if you turn helium into hydrogen, what's that?
Miniature nuke.
Fission.
Yes.
Where does fission take place in a perfect cycle all the time, constantly? James? The sun. That's why the sun is so hot. Yes. All right. So moving on. No clear boundary. It just sort of floats off into space. Fewer and fewer molecules until you're up in space. All right. We saw this dude earlier. I played him for everybody, so I can skip him. I love him though. I think he spent a lot of time at Ren Fests. You know what I mean? Like a lot. So here we have humidity and relative humidity. Okay. What's the first one here? The amount of water vapor in the air. What's that one? Alex?
Humidity.
Humidity. All right. So the ratio of water vapor in a volume of air relative to how much, there you go, relative to how much water vapor the volume air is capable of holding is your relative humidity. Well, that's right there. So if you have, say, a container and it's full of gas, but that gas can hold, let's say, 10 liters of water. It's a big container. Okay, it can hold 10 liters of water. And then you put 8 liters of water in it. Your humidity would be 8, but your relative humidity is going to be a percentage. So it's a ratio of how much there is versus how much it can hold. So at that point, it would be 80%, right? It's going to be 80% full. So 80% is your relative humidity versus your humidity, which is just how much water's there at all. So cloud formation. All right, clouds form when moist air rises, expands, you know this, then it cools down and you get all this condensation, and then the water gets heavy. Oh, and it comes, there's a little condensation nuclei, which is something all the condensation forms around, like this little dust particle right here. And then it all comes falling down as precipitation. Yeah, precipitation. All right, so cloud formation. This is interesting. So mountains can affect the weather greatly. Okay, so clouds can form when your wind hits a mountain and has no place to go. So wind can't go anywhere, it's at a barrier. So as that wind, which has got water vapor in it, hits, sooner or later it all piles up together and you can get a cloud on one side of the mountain. And that side of the mountain can get a lot of rain. Depending upon your typical weather patterns and how your wind typically flows, you might have one side of the mountain that they call a rain shadow, like right here, where it just doesn't get rain because the other side gets all of it.
I think we saw something like that in Hawaii.
Did you?
From
Mhm.
a helicopter.
Yeah.
Part of it was like the.
Yeah. So it's interesting, but yeah, you can get mountains that, you know, the rain will come and it will just rain because the wind full of water vapor has nowhere to go. And on the other side, it's just dry. So you get what's called a rain shadow. Now, when the rain hits the mountain and doesn't go anywhere, it starts to kind of circle up and form a cloud. Does anybody know what that's called?
Cloud formation.
Warm air cools, water vapor condenses, cloud forms, but due to a mountain, do you know?
Lifting.
Some kind of lifting, you're real close.
From.
Yeah, orthographic lifting. That's a good one, Caitlin. Excellent. Orthographic lifting, that's what that's called. Orthographic is like mountain formation, basically. So orthographic lifting.
That's
Now, here you go.
holographic.
Anybody interested in being a pilot or just sitting there in a plane? You ever been in a plane with turbulence? You ever been in a plane with so much turbulence you thought you were going to die because you're flying along and the plane goes and it drops? That is terrifying, right? And really, it's fine. They know what they're doing, but it's very scary feeling.
The previous slide, it said orographic. Is it orographic or?
Ortho should have a, oh, I'll fix it. Yeah, should have a TH in there. I'll fix that one. Thank you. So, yeah, it should. Oh, yes. Or, go back. Yeah, see, now I'm gonna fix it and it's gonna be weird on me. So if you've been in a plane where you've got enough turbulence that you're feeling like the plane is dropping, like it's kind of like when you're on a roller coaster or anything, whoop, and you have that feeling of
Weightlessness.
yeah, it's weightless for a second and it's not a fun feeling. It's like, okay, let's not do this. I don't like it. I was on a plane once that was like that and it was scary. It was very scary. And there are people screaming in the back, which didn't make it any less scary because you're like, people, you're not helping. So yes, that it's a weird feeling. So if you look, I'll do that later because it's going to be stupid right now. It doesn't like to work when I have the
It's just a prank, bro.
mouse going. Yeah, prank bro. Yeah, no. What? I didn't hit that. Oh, shoot. Sorry, 1 second. It thinks I did something. I didn't do that. Stop. I hit this one, not the other one. So yes, you got light, you got some light turbulence. You might rise and drop a meter. And you feel that a little bit, kind of like this. Bumpy, bumpy, bumpy. Not bad. You won't really notice it. But if you're dropping 3 to 6 meters, you feel that one. And if you're dropping up to 30 meters, you really feel that. And this is when they're like, put on belts. They start doing that when you get to like 3 to 6. Yeah. Because the pressure, you run into turbulence where you've got like uneven pressure, uneven density in the air, and the planes just bump around. Bumpity, bumpity, bump. So yes, cloud formation. Now we have a general idea of how that functions, but if you look here, there's a lot to do with stability of air masses. So how much is an air mass able to resist rising? And that is determined by how rapidly it's cooling, temperature of the surrounding air. And then you have this going on too. You have, oh, it is oro, not ortho. And I'll go back and fix it again. See, I said it wrong. Orographic lifting. You have, I don't know what's in my head today, y'all. And then you have this thing called a connective lift where you've got moist air, cool air coming behind it, one another. And then you have this convergent lift.
Convective, not
Yeah.
convective.
That's what I said, convective, didn't I?
I heard connective.
Connective. I'm telling y'all, it's been a week. Convective, where you have the air coming together, convective, and then convergent, where you've got it cool air coming at the same time. So all these different things, all these different processes affect the stability of the air mass and cloud formation. You've also got latent heat. So heat's going to cause things to rise and expand, right? And then you've also got, well, that's latent heat. So latent heat is energy stored in, what now?
It's a blind cat rising into the air.
It does look like that. So latent heat is the energy stored in the water vapor, and like how much energy do you still have as the water vapor rises? Is it still warm? Is it warming up the molecules around it? Lots of stuff involved in cloud formation. All right, now, types of clouds. I want you to remember, there's Rico, that clouds are classified by both altitude and shape. And usually you can put those two parts together and get the name of the cloud, but not always. Usually you can. So this dude, I wanted to get a picture of him, but I didn't get one in time. This dude, Luke Howard, 1803, decides how we categorize clouds. When you see one like this cumulonimbus, sometimes people call them a thunderhead. You might see that sometimes. All right, so you've got the height. Now the height is impacted by obviously pressure and temperature, and clouds that are up high versus clouds that are in the middle range versus clouds at the top. So what do you call the ones that are up very high? What's the root you use for them? Drew.
High clouds.
Bailey. Close. Alex.
Sir goes left, sir.
Yeah, okay. So see this one at the top that say, they say zero. See them? 0, 0, 0 up there. And that also has to do with their shape. And you'll see that too. So then what are the ones in the middle? That's Bailey said. Oh, no, almost. You almost said it. So the ones that's the use of the bottom. The ones in the middle are called what? Alto. These are the alto ones. And then the ones at the bottom are, that's what Bailey said a minute ago, the strato ones. Remember, the stratosphere is low. So you have these guys that are low. They tend to be flat. That's different. They tend to be flat. Those are the strato ones. And then you can have strato ones that are up here, like alto strato. Well, what does that mean? Well, it's kind of in the middle. So then you've got these guys too. You got the ones that are classified by shape. Let's pack these in here. So the ones that mean hair, they're wispy. What do we call those? Anybody know? So again, these are the cirrus, same root. These tend to be very high. When you see cirrus clouds, or this is a cirrostratus because it's kind of packed together. And then this is cirrus. And
That's why it's called that.
yeah, because they're
There's
up.
a company called Cirrus.
Yeah, they're up. So what company?
Airplane.
Airplane. Smart. They're up really high. And then these guys is cirrocumulus. Sorry. These are up high too, but they have a different shape. So the cirro meaning high, stratus is the shape here because it's flat. Cumulus is the shape here. So what means pile or heap, puffy, lumpy looking? Which one is this? James? Cumulus. So think about it, accumulate. If you put things in a pile, you accumulate them, right? So that is where you get cumulus from. And if you were asked, or you asked a kindergartner to draw a cloud on it, draw me a cloud, that's what they're going to draw. The puffy ones, the cotton ball clouds, right? These are the ones that you go, oh, I see a whatever shape in the clouds. Oh, it's the baby Jesus, it's the Virgin Mary. Whatever you've seen in the clouds is there, right?
Waka.
Ah, so how about layer? What means layer? Bailey?
Yes, how's food?
This one's actually, this is your stratus again. So it's similar to the strato, which tend to be the low ones. Stratus, these are the ones that are they're like a layer. So a strata, if you've ever had a strata, it's like a breakfast casserole that's layered with egg and cheese and veggies and whatever else. Or sometimes it's bread, you can layer it in and bake it like a quiche or like a French toast bake. That's a strata. And there's lots of desserts that are named after layers like that. People put cakes in layers. And then this last one means cloud. Anybody know what this one means? Okay.
Cloud.
Nimbus. Where else have you seen nimbus? James.
There was a TV show called The Then Maddie, and there is a news reporter whose last name is Nicholas. His first name is John.
Huh. Where else have you seen it, Chloe? Harry Potter. What's he ride?
2000.
A Nimbus 2000. What was his first one called? Firebolt. Second one was the Nimbus 2000. Nimbus means cloud.
He got Nimbus and that broke down and he got the Firebolt. So Firebolt was second.
Yeah.
Oh yeah, you're right. Sorry, the other way around. I'm telling you guys, my brain is so dead today. Yeah, Nimbus 2000. No, Firebolt was first.
No.
Are you sure?
Firebolt was what Sirius gave him in book 3.
Yeah. Okay.
Nimbus 2000 was
So the first one was, what was the first one then?
Nimbus.
It was a Nimbus, but not a Nimbus 2000. That's right. I don't mess up Harry Potter, so my brain is definitely whacking out on me today. All right, so yes. So Nimbus, cloud, think about it that way. All right, so then you can have different kinds of clouds. All right, so stratocumulus, these are the ones that cover much or all of the sky. When you go outside and it's just gray, that is your stratocumulus. And so there's a word here I'm looking for. It is
Depressed.
low. They're going to be low. So where are the altocumulus clouds going to be, Bailey? In the middle. And then get off the arm of the chair, please. Where are, all right, Sky, where are the cirrus ones going to be? Yeah, got it. So they're high. So there you have, boom. So you have different levels of clouds and you can know, generally where to find them, and you'll learn what kind of weather to expect with them. We'll be doing a lab in the next couple weeks where we have a weather station that's going to be, the only thing is it's not attached somewhere yet, but it's going to be attached. And it's a weather station that will communicate with the website, and you all will be able to go online every day and get the weather data. And you guys are going to predict what the weather will be based on the weather data. And you're going to keep a log for like a week. It should be really interesting to see what happens. So precipitation. All right. So you have the process in which cloud droplets collide together and they join to form a larger droplet. Anybody know what that is? Alex?
Coalescence.
That's coalescence. Excellent. And then when you have, just your stack's gonna fall over. And then when you have all forms of water, both solid and liquid, rain, sleet, snow, and hail, what's this, Bailey? That's precipitation, right? Okay, so if you look closely here, this is how a snowflake forms. These little water molecules, they start to coalesce, and then the way they attach to one another is what causes, there's always 6, but it has to do with the molecular structure of water. And I actually have a really cool video about that too. So you guys know the water cycle, blah, blah, blah. You've been over it 100 times, right? You know what happens here. You got this constant movement of water back and forth, goes up, comes down. The same water that's here is the same water that's always been here. Unless you're doing weird electrolysis stuff, then yeah,
There's some meteors.
Yeah,
in water,
that kind of
right?
business. Yeah, meteors maybe, not a whole ton of stuff. It just kind of happens. All right, so this is the last thing, but I want you to really, really watch this. Now, I told the other class too, remember, we're in a new quarter now. Be sure you check your stuff and be sure you have turned in everything, because I have to give you your final grades for this first quarter. And if you're missing something, it'll ding you pretty hard. I noticed on the test, there was the image you got it. You were the first one who got it. I had it uploaded for everybody else then. And then the first one on the test, the answer was checked wrong in there. So everybody got that wrong, but everybody really got it right. But there was one thing on the lab, real quick, that I think everybody or almost everybody got wrong. So, the lab we just finished, 9 with the, no, 10 with the sand blowing. Is that 9? 9. 9, it's 9 with the wind blowing it, the sand. So the question asked about which side of the dune is steeper, where does the deposition and erosion take place? So if you do, one second, go there, go there. Oh, now go there in the middle. Holy moly. Okay, let's just go back here. This is making me crazy. We'll just insert new slide, get a blank slide. Alrighty, now I don't have my, oh, I think it's right here. My stylus. It's way easier to draw with that than it is either in this one or the other one. It's here. So, okay, let's see. You have wind blowing and there's sand here, okay? And you have wind blowing this way at it, all this direction. All right. Your dune is going to form. And it's going to form by the sand getting kicked up this way, right? Eventually, your dune is going to look like this. Which side is steeper, windward or leeward? Which side? Okay, first off, which side here is windward, right or left?
Left.
This is windward. Yeah, jiggling. And this one's leeward, right? All right. So what's going to happen here, what had happened was, as your wind blows, it's going to form a dune where your deposition, okay, so your wind's going this way, you have this dune, whoop. Your leeward side is steeper, your windward side is less steep. Where's the deposition taking place? On the windward side? On the leeward side. So here is your wind. So this side is your erosion. It's very hard to write with this thing. And this side is your deposition. Because it's blowing up the sand and the particles are falling like this, steeper and steeper. And it'll continue to blow here, so it will continue to erode. Like it'll push the sand, it'll push the sand here, but then it'll keep blowing it over. So you'll get this little leeward side is going to be steeper than the windward side. And since everybody had a hard time with that, and
earthquake happens over sand dunes, well, it just kind of like.
You just shake away, I guess. I don't know. It's a great question. I've never considered that. So remember this because it's an important concept to understand when it comes to how fluids move. And because you should remember it, you might want to, like really remember it in case it shows up on a test sometime. So here is how snowflakes are formed. This is super, super ultra fascinating.
You are a beautiful and unique snowflake. You are not a beautiful and unique snowflake. No one else is exactly like you. You're one in a billion. You realize that means there's like 8 people exactly like you? Shut up. I am a unique snowflake. That's so cheesy. There's a lot of snowflake science videos out there on YouTube, and they all mention the same idea, that no 2 snowflakes are alike. But where do we get that idea? The universe is a big place. It's really old, and countless planets with countless snowflakes. Surely 2 of them have been alike. The idea that no 2 snowflakes are alike probably started on January 15, 1885 in Jericho, Vermont. A 20-year-old named Wilson Bentley was sitting outside his farmhouse, freezing his Bentleys off, holding a sheet of black fiber and a turkey feather in the other hand, waiting for a snowflake to fall in just the right spot. And when it did, he put that snowflake under a microscope attached to an enormous old camera, and he held his breath. One wrong breath could ruin the whole thing. He opened the shutter, and Wilson Bentley had the first photograph of a snowflake ever taken. Wilson Bentley, seriously loved snowflakes, in the sense that he never got married, never moved out of his mom's house, and basically just took pictures of snowflakes for 50 years. Now, he called them masterpieces of design. Of course, we know there is no design in a snowflake, but that doesn't make them any less amazing. Every plate, every branch, every needle on a needle on a needle, all of those details are what's called emergent properties. This is complexity that's based on very simple rules. And for snowflakes, those rules go back to the basic laws of physics. In the air or in liquid, water molecules are zipping around, bouncing off of each other and everything else trillions of times per second. We have no way of knowing where they are or what direction they're facing at any moment. As we remove heat, it gets colder, and those water molecules start to slow down. Eventually, their atomic attraction, the actual hydrogen bonds between water molecules, takes over and they settle into order. It sounds complicated, but we just call that freezing. The structure of a snowflake can be found in just 6 water molecules. I know that the angle between any 2 hydrogens is about 105 degrees. And I know that's true for any water molecule in the entire universe. And for some of those water molecules, well, the other hydrogen's behind them. Just like that, we've uncovered the 6-fold symmetry of a snowflake crystal. That crystal starts as a tiny speck of dust or pollen, which catches water vapor out of the air and eventually forms the simplest of snowflake shapes, tiny hexagons called diamond dust. And then randomness takes over. There's a very simple reason why a snowflake's arm grows out here and not here. It's just because it sticks out farther and has a higher probability that water molecules will land there. And more water molecules land. And then we got an arm and another arm and another arm and on until we get the intricate and beautiful shapes that we know and love. Depending on temperature and humidity, and a lot of factors that scientists don't even understand, those simple hexagons can give rise to seemingly infinite shapes. And each snowflake will travel through different air currents and bump into different water molecules. But in 1988, researcher Nancy Knight claimed to find 2 identical snowflakes, and they do look very much alike. It's quite possible that 2 of those simple hexagons could be the same in every measurement of size and mass, but they would not be identical, and physics tells us why. We know that water molecules are made of 2 hydrogen atoms and an oxygen atom, but not every hydrogen is created equal. If we go back to the Big Bang, we find out that out of every million or so hydrogen atoms created, a couple hundred of them, instead of just being a proton and an electron, are holding on to a neutron. And this is the isotope of hydrogen called deuterium. In Earth's water, even in you, about 1 in 3,000 molecules will be holding on to deuterium instead of hydrogen. Out of the million molecules that make up a snowflake, a lot of them will be holding on to deuterium too. Even identical looking snowflakes are not the same. Now, you could love a snowflake just because it's pretty, but it doesn't take away from its beauty to understand that it was sculpted by chance and physics. To me, that adds to the beauty. I have to say, this whole "we are unique snowflakes" thing is pretty cheesy. It might be the most overused metaphor in the history of metaphors. So let me give you a new one. Snowflakes are symmetrical, but they're not perfect. They're ordered, but they're created in disorder. Every random branch retells their history, that singular journey that they took to get here. And most of all, they're fleeting and temporary. Even if sometimes they don't look so unique on the outside, if we look within, we can see that they're truly unique after all. Stay curious. We're not the only social animals that sit down and eat together, but we are the only ones who cook.
That's interesting. Very
We
interesting.
have no way.
They're never the same, even though they might look the same. So we're all special snowflakes, like he said. So yeah. So anyway, it is almost time for y'all to head out. So it's 1:22. So that would be good for you guys to start hitting the candy machine before you go. Before you go, please clean up the lab area by putting all the utensils and tools back in the containers and collect all the bottles for me to recycle and then put all the trash together on another tray and take your money. Lily, don't worry about lab. I'm gonna post a graph and stuff so you can see what happened. And same for Liam and Jack.
Okay, perfect.
All right, I'm gonna turn y'all off. I'll catch you later.
All right, bye.
Later, bye-bye. Whoa.
With the lab I was supposed to turn in last week, but I wasn't.
Okay, yeah.
This morning I left it on the table, and there happened to be a jack-o'-lantern on the table, and it collapsed and rotted. And I got pumpkin slime all over it, and I have
This is
extra-
bad.